Welcome to the 1963 Nobel Prize in Physics, which was divided between two projects and three people, which we'll get to that in a second. But it's important to remember with this one that the understanding of what was actually in a nucleus, in fact, the discovery of the proton and the neutron themselves was not that long before this particular project. So what these people did was truly incredible and groundbreaking. This is phenomenal stuff. They're understanding really what is going on inside that nucleus, of every atom in the universe, was incredible based on how long these things had actually been understanding what was even in there, much less their overall behavior. So, and also remember, we're still a year away. This prize was done for work was awarded for work that was 5 or 10 years before this, in some cases maybe 20. But we're still a year away from the discovery of the quark. So the world still doesn't know that there's something smaller than a proton or a neutron, right? So we're still in that land of discovery. And remember, 1963 is not that long ago. I mean, it's only 9 years before I was born, and we still hadn't discovered the quark. That was coming after that. So we're coming into some more modern stuff, but it's amazing just how far we've come, how fast. Now, Eugene Wigner was somebody who won essentially half the prize because he was one of the two projects that the prize was divided amongst. And he won for his contributions to the theory of the atomic nucleus and for the elementary particles in it, right? So, and particularly for his discovery and application of fundamental symmetry principle. And I'll explain kind of what he did in a minute. That's all a bunch of gobbledygook at the moment, but I can make it a lot more simple. So that's the official prize wording. But let's look at the other half of the project. Was shared between two people, Maria Mayer, who was the second woman to win the Nobel Prize, and she actually worked on the Manhattan Project, as did Eugene Wigner. And the first woman to win, as you recall, was Marie Curie, way back at the beginning of these awards. The other person on this project was a gentleman named Hans Jenson, and they won for their discovery of concerning nuclear shell structure. Now, remember, we've got electronic scale shell structure. That's electrons around the nucleus, but the nucleus itself actually has a shell-like structure, and we'll get to that in a minute. Now, remember, the neutron wasn't discovered until 1932, so this is just sort of the prize itself that they won was just 30 years after even the discovery of the neutron. So the world was in this great discovery mode of the nuclear world, and Maria Mayer actually we're going to hear from her here in her own words in a little bit of her explaining how things inside the nucleus work to Enrico Fermi of all peoples, who won the prize, and I think it was 1932. So we're not talking about science, these are science powerhouses, right? These are people who really knew what they were doing and have tons of things named after them. So let us dive right in with Professor Wigner and what he did to earn this prize. So after the discovery of the neutron, scientists all over the world were busy peeling back layers of just atomic mystery after atomic mystery to really unveil the absolute truth of what's going on inside the nucleus of an atom. So imagine this, you're physicist Eugene Wigner, and you're thrust into this world of understanding and trying to reveal what's going on in the nucleus. And it before that, people were just thinking of it as like this haphazard clump of positively charged particles. And but it really is a dynamic arena where protons and neutrons collectively are called nucleons, kind of deal with these different forms of attraction. And Wigner discovered that the force of, sort of like glue holding the nucleus together isn't just sort of normal. It's a little bit different than most other forces. It's sort of this phenomena of just really big extremes. So when nucleons are far apart, protons and neutrons are far apart from each other on an atomic scale, not on a galactic scale, right? So not like, hey, Dallas is far from Cincinnati, right? That's not the same. We're talking about far apart on a nuclear scale, which is different. But when you're far apart, there's barely any interaction. There's barely any attraction between them. It's called weak. But when you get close together and you get them in tight with each other, bam, this force is it's huge. It's amazingly large. And that's why when you split the atom, there's so much energy that comes out of it because of that strong nuclear force. Now, Wigner also discovered some other things. He didn't, the nuclear force doesn't care whether it's a proton or a neutron, it treats them both exactly the same. It has this symmetry. In fact, it was a symmetry. He used symmetry to really explain all this stuff. So the nuclear force is not picky about electric charge, positive charge, neutral charge. It doesn't care. Nucleons get close to each other, and that strong nuclear force or the weak nuclear force is the same without regard to charge. So it's important to know that he did kind of unleash a lot on us, because who would have thought that neutrally charged things and positively charged things, the forces act the same on them? But sure enough, it does. Which, if your only background is in electromagnetics, that doesn't make any sense. You're kind of like, well, who cares about that? But in a nuclear force sense, that's the way it works. So let us dive into the other half of this prize, which I think is equally interesting and will unveil some things that I'm not sure are really widely known, but inside the atomic world are very widely known. So let's take a look. Okay, now remember, in modern physics, the nucleus of an atom consists of nucleons. That's just a goofy word for protons and neutrons. Those are both different types of nucleons. And those are surrounded by electrons distributed within certain shells. They can only exist inside certain shells. You don't get an electron in a 1.5 state. You only get them in different shells, different discrete quantized values of space away from the nucleus. It became apparent when they were working on this that the atomic nuclei, um, in which the number of nucleons corresponds to full electron shells, are incredibly stable. So if you have, like, carbon is incredibly stable, hydrogen incredibly stable, different atoms are incredibly stable, but it's ones where you have full electron shells equaling the exact number of nucleons. So certain types of take helium, which has two protons and two neutrons, is incredibly stable. Different forms of helium that don't have those same, equal number of nucleons to nucleon pairs to electrons are not as stable. So they came up with this model to understand really how these things work. And the model they came up with reflected the observations and behaviors that they were seeing as nucleons rotated around their own axis and around the center of the nucleus. So what does that really mean, right? So their model reflects this observation of directions with nucleons rotating around their own axis and around the centers of the nucleus. Well, that doesn't make any sense, right? It's a little bit confusing. So Maria, who won the prize, had to explain this to Enrico Fermi, of all people. And I want to use her own words so that it's a little more clear, because she said it perfectly. So a little background on this. So Maria had this way of explaining things where she spoke very quickly and just kind of got it out and said, here you go on with your day. Enrico Fermi was a completely different kind of person. He liked people to go slow and methodical and explain things to him in a specific way, which is fine. Everybody has their own way of communicating. Now, I want to use her own words as she was trying to explain this to Enrico Fermi, because she went very quickly, like I did a minute ago, and said, it's just like this. And he goes, well, explain it to me a little bit differently. And she kind of off the cuff, so the story goes, came up with this particular explanation. And these are her own words. Think of a room full of waltzers. Suppose they are going round the room in circles, each circle enclosed within another circle. Then imagine that each circle you can fit twice as many dancers by having one pair go clockwise, another pair go counterclockwise. Then add one more variation. All the dancers are spinning, twirling round and round like tops as they circle the room, each pair twirling and circling. But only some of those that go counterclockwise are twirling counterclockwise. Others are twirling clockwise while circling counterclockwise. The same is true of those dancing around clockwise. Some twirl clockwise while others twirl counterclockwise. So that's really kind of explains how the things happen inside the nucleus. You actually do have these shells of nucleons that are spinning around and then rotating. They do all kinds of things. It's not just a stable clump of stuff. Every once in a while, you'll see a video where the nucleus is kind of just moving around and doing stuff. And that's really what it looks like. It really does kind of move around and do things, much like people dancing in a ballroom. So that is the nucleus of the atom in Maria's own words. Now, remember, they were doing this work in a time when the electron microscope was kind of the techniques to actually build an electron microscope were kind of in their infancy. There's no way to image this stuff. This is just purely based on secondary observations of behavior. But it turns out that in 2024, we have the technology to really look at these things and go, yeah, that's really how it works. So these people came up with the mathematical descriptions based on, hey, let's take this other effect and try to infer what went on to get to that answer. And she was one of the brilliant ones in the field, as rewarded by the Nobel Prize. She was the second woman ever to win one. To date, there's been five, I think. Most of those, three of those have been in the last sort of 5 or 10 years. But she was the second. Marie Curie was the first. And Marie Curie, by the way, wasn't just the first woman to win a Nobel Prize. She was, but she was also the first person, man or woman, to win two Nobel Prizes ever. And she actually won them in different fields, one in physics, one in chemistry. So some interesting history here in this prize. And it's a little difficult to come up with graphics for this kind of stuff, but I hope this discussion has kind of helped you understand really what does go on inside that nucleus, which is some pretty cool stuff. So I hope we'll see you on the next video. And I hope you don't forget to click like and subscribe. Really does help us out with those algorithms, and we'll see you soon.